Now, why did you want to write a book about calculus? Actually, wait a minute. I got a different question. Why did you want people to read a book about calculus?
Well, I've been in love with the subject since high school, so there's the giving side of me that wants to give this gift to the world. But I really do think it's one of the great ideas of all time. And if folks could appreciate that, I think it will enrich their life. They'll see things through the lens that I see. I see calculus everywhere, almost like that kid in The Sixth Sense who says, I see dead people. I look around, I see calculus.
Well, take me through that. I mean, how does calculus come into our everyday lives, not just as a fascination for you?
Oh, almost anything you look at in your kitchen or in your house, there's calculus under the hood. Let's say your microwave oven. What's going on in there? There's invisible waves of energy, the microwaves. And as we all know, they have hot spots and cold spots. If you don't have one of those rotating turntables in there, you're going to burn your mouth, in certain places in the soup. But the reason for the patterns of hot spots and cold spots is that the microwaves that form a pattern in the cavity of the microwave oven that can jiggle those water molecules in the food and make, obviously, makes your food hot very quickly. But the understanding of those wave patterns and how we can control microwaves, all of that is built on the math of calculus.
Well, let's start at the beginning. What exactly is calculus?
Well, if you had to say it in a word, it's the mathematics of change. When you have something that's constantly changing, especially if it's changing in changing ways, like, for instance, imagine a ball rolling down a ramp. Not the most exciting thing in the world to think about. But what's interesting about it is that it picks up speed as it rolls. It doesn't just cruise down at a constant speed. It rolls faster and faster and faster. If you drop a rock off a bridge, at first it's not moving, and then it picks up speed and it accelerates. There was a time when humanity didn't understand the laws of falling objects. And, that had to be figured out by Galileo in the 1600s. And the math to do it didn't really exist at the time. And that led to what we nowadays would call differential calculus. Now, that, again, it doesn't sound like that's much of a payoff. You can understand how things roll down a ramp. But today we use differential calculus to understand the level of virus in the bloodstream of a patient with HIV. When we invented triple combination therapy to turn AIDS from what used to be a near certain death sentence now into a manageable, though chronic illness, calculus was a big part in figuring out the triple combination therapy that has been a lifesaver for millions of people.
Well, you describe in your book not only how it's about change, but how it's about curves and figuring out areas and curves and things. And you talk about how infinity turns out to be critical for calculus. Tell me about that. Why do you need infinity?
Right. So it's definitely true that infinity is a key player in thinking about change of any kind. So when you're dealing with a curved shape, something's changing there. What is a curve? It's something that changes direction, right? If it didn't change direction, it'd be going in a straight line. So when you have curves, you're talking about a certain kind of change, a change of direction, and that makes the math difficult. We did a lot of questions in school about triangles and squares and other shapes that are made up of straight lines. But when you have something like a circle or a parabola or any other curve, it's very difficult to do calculations of like the area under the curve or so-called tangent line to the curve. Those things are hard because they're not made up of straight lines. It's an obvious point that a circle is round. It doesn't contain any little straight segments. But in calculus, we pretend that it does. We like to pretend that a circle, like if you zoomed in on it under a microscope, you'd see that the circle will start to look straighter and straighter under increasing magnification. And it's almost as if it were made up of infinitely many, infinitesimally small, straight pieces. So this is the great brainstorm of calculus. Think about an object that's complicated or a motion that's complicated, like that accelerated motion I mentioned earlier, and pretend it's made up of simple, much simpler pieces at the cost of having to imagine infinitely many of them. So harnessing infinity turned out to be the key to solving lots of problems that were previously intractable.
And you take that farther in your book, right up to modern graphics, computer graphics, which use many little tiny straight lines to make animations.
Yeah, that's right. That's a great example. So if you think about Shrek or Toy Story or Avatar, any of those computer-generated movies, what's going on if you dive deep into the computer graphics is that say, Shrek's round belly is actually made up of millions of polygons, triangles and squares and things. They're so tiny you don't see them. You don't perceive that his belly is faceted. It looks smooth. But in the computer, we represent any sort of shape using an enormous aggregation of triangles and other rectilinear shapes. And so this is a great insight of calculus. So you can represent anything curved by thinking of it as an infinite combination of these infinitesimally small but straight shapes.
That's an interesting trick. If you can't deal with a curve, pretend it's straight lines, just a lot of them.
Well, it's very creative. I do love that. I'm glad you pick up on that. There's a creative fantasy in calculus that I can't deal with a curve. Well, it's not a curve. It's made up of lots of straight lines. Not just for things like computer graphics, in movies, that's sort of whimsical in a way. It's entertaining, but not that important ultimately. But we've also used the same idea to improve facial surgery. Think of someone whose chin is malformed and it's sticking way out, and they go to the surgeon and say, could you fix my face? With the help of computer graphics and computer simulations of the soft tissue in a person's inside their skull, they can figure out if they take out certain bones and then sew you back up what your new face is going to look like. And it's with the help of calculus that now surgeons have what is in effect like a flight simulator for facial surgery.
Well, I get it that if you have one problem that you can't solve, you solve it by making an infinite number of smaller problems, but now you got an infinite number of problems. I mean, that still sounds large.
Well, the strategy comes with a cost, as you say, that when you divide a hard problem into an infinite number of smaller and hopefully easier problems, you're still stuck with this infinity of small problems. And now you got to put them back together to solve the original problem. So that's the other half of calculus. That's the part we call integral calculus, where you have to integrate all the answers back into an integrated, coherent whole. And that is the harder part of calculus, and it's the part that certainly our students find more difficult. So in the old days, I'm talking about in the days of Archimedes in ancient Greece, like 250 BC, he did it because he was one of the smartest people of all time. He could do it in his head. He could do it with tremendous ingenuity. But in modern times, like fast forward almost 2,000 years after him to Isaac Newton in England or Gottfried Leibniz in Germany, they found a trick that nowadays we call the fundamental theorem of calculus, which probably we don't need to go into right here, but it's a way of making calculations so much faster and so streamlined that you could teach them to ordinary high school students. So that's when people take calculus in high school now. They're learning the great advance of Newton and Leibniz that makes calculus quite doable, even by people of ordinary, dare I say, ordinary intellect.
You spent about half your book delving into the history of calculus and mathematics, and it goes back a lot farther than I thought. I mean, you mentioned Archimedes. That's the ancient Greeks. This has got a long history to it.
Mm-hmm. It's not traditional to put it this way. I mean, it's normally phrased that calculus is a creation of the mid-1600s, as I say, from Newton and Leibniz. But you can definitely see precursors of their ideas 2,000 years earlier in the work of Archimedes, who is thinking about the strategic use of infinity to solve what for him were geometry problems about curved shapes like circles and spheres and parabolas and things like that. So his skillful use of infinity then in the Renaissance and later gets used to solve problems about motion, how things move on the earth, like I talked about the ball rolling down the ramp, but age-old mysteries about how the planets move in the sky, why the comets behave the way they do, and so on. So all these things were then the next great success story of calculus, figuring out problems in astronomy and earthly motion.
You spent a lot of time talking about Isaac Newton and his revolutionary thoughts in calculus, and you give him a lot of credit for the Industrial Revolution. Take me through that.
Well, I think so, because Newton, if you had to say in a word what was his big contribution, people would often say, well, the law of gravity or his laws of motion. Sure, those were great, but I think his biggest advance was the revelation that nature is logical, that you could use logic in the form of math, specifically in the form of calculus, to predict how nature would unfold. And we didn't really know that. I mean, until Newton, we had seen mathematical patterns in things like music, certainly in charting the motions of the planets, but we couldn't really predict very well. We couldn't anticipate the future until this tool of calculus was refashioned by Newton into this incredible soothsaying instrument, and that because you could predict the future and because laws of nature did exist, as he showed, well, then the hunt was on for other kinds of laws of nature. So there were laws discovered about how electricity works or magnetism. And in a matter of just a few decades after those things were figured out, we had Marconi, creating the telegraph and sending wireless messages across the ocean. So cell phones and TV and radio, those are just a short hop and a skip from that kind of work. And so that's the thing. Once you have Newton showing that the universe is logical, everybody's looking for the laws of not just electricity and magnetism, but how air flows. Pretty soon you get people working on airplanes and lift and so on. I mean, every part of nature has been mathematized, and that's given us enormous control over our world and helped to create the modern world as we know it.
Now, calculus also featured in a Hollywood movie a couple of years ago about the space program.
Oh, it sure did. Yeah, that's right. Hidden Figures is the great story of the women African-American mathematicians working for the precursor of NASA, and then eventually it became NASA. It was people like Katherine Johnson, who's sort of the star of the movie. She's still alive in her, I think she just recently had her 100th birthday. She and her colleagues helped to put the first human beings on the moon by doing trajectory design for the Mercury program and later the Apollo program. And all of that, when they say it's not rocket science, well, that was rocket science. And it was rocket science using calculus. And as the movie shows, it was her knowledge of calculus and Newtonian gravitational effects, and including things that went beyond what Newton had done, by the way. I mean, Katherine Johnson did not assume, as Isaac Newton did, that the Earth was a perfect sphere. She knew that, and so did Newton, by the way, they knew that the Earth was a little bit flattened at the poles and bulging at the equator. But taking subtle effects like that into account were really important, or else John Glenn, when he returned to Earth, might have predicted that he'd be landing hundreds of miles in the Atlantic Ocean away from where he did land. And it was, a bobbing astronaut in the ocean can drown. That kind of stuff you don't want to fool around with. You've got to know where the person's going to land and be right there when they hit. Use calculus in a crucial way in the space program.
And do you assume that Elon Musk uses calculus today to make those precise landings of his rocket boosters that come back to pinpoint landings in Florida?
I mean, certainly that it is the math of the universe. We use it all the time in every domain. There's nothing that has superseded calculus. It's still, it may be old, but there's no need to replace it. It works. This is the way the universe really works. Even in quantum mechanics, we have this very sophisticated modern subject now for atomic physics and subatomic physics. And even though it has been revolutionary in its physical principles, the math of quantum theory is still calculus.
Well, it's hard for those of us who've been out of school for a long time and don't use advanced math as a tool in our everyday lives to really appreciate something like calculus. So what's the one thing you would want people to understand about it?
Well, I would say that it's not, you might imagine it as cut and dried, that it's very mechanical, it's very black and white. I would like people to come away understanding what a triumph of human creativity and imagination it is. That it's built on this one vision that we can cut things into finer and finer pieces all the way down to the infinitesimally fine. And what I find so wonderful about that is that it's not really true. We know that there's a smallest thing. We know that there are atoms. And yet, by pretending that we can divide everything infinitely finely, even though that's only approximately true, it works so well that it has been a revolutionary idea. And I mean, it has really changed the world. So I find something almost poetic in it that, Picasso has this quote that I like where he says, "Art is the lie that makes us realize the truth." And I think calculus is a little bit like that. It's built on a lie that the universe is continuous and infinitely subdivisible. It's not really true, and yet it's such a beautiful vision, and it comes so close to being true that it works.
It's the language of the universe.
Well, I like to call it that. Yeah, I think so.
Dr. Strogatz, thank you very much for your time.
Oh, it's been a great pleasure, Bob. Thank you.
Dr. Stephen Strogatz is a professor of mathematics at Cornell University in Ithaca, New York. His new book is called